Around 1800s, a physicist named Thomas Young, using his famous double-slit experiment, showed that light creates interference patterns like water waves. This proved light behaves like a wave. But in 1905, Albert Einstein showed that light is made of tiny energy packets called photons. This breakthrough helped explain the photoelectric effect, a phenomenon where shining light on certain metals causes them to eject electrons. Classical wave theory couldn't fully explain why light below a certain frequency, no matter how intense, failed to knock electrons out. This idea made perfect sense only if light behaved like a particle, not just a wave, and it earned Einstein the Nobel Prize in Physics in 1921. But then came an even more surprising question. If waves like light can act like particles, can particles like matter act like waves? In 1924, Louis de Broglie proposed that all matter, like electrons, atoms, or even larger objects, should also have wave-like properties. This idea, known as matter-wave duality, suggested that every particle has a wavelength. Later experiments confirmed this. Even electrons can create interference patterns, just like light waves. Now that we understand the dual nature of the universe, we return to our earlier puzzle. How can light, or photons, have energy if they have no mass? The answer lies in momentum. These photons travel at the speed of light. But wait, this raises a natural question. How can something without mass have momentum? In classical physics, momentum is defined as P equals mass times velocity. So if the mass is zero, as in the case for photons, this would suggest their momentum is also zero. The answer comes from quantum physics. In the year 1900, Max Planck discovered that the energy of a photon depends entirely on its frequency, or how fast the wave is oscillating. He introduced a very simple relationship. Energy is equal to a constant, called Planck's constant, multiplied by the frequency. In symbols, this is written as E equals h times F, where E is energy, h is Planck's constant, and F is the frequency of the photon. This means that blue light, which has a higher frequency, carries more energy than red light, which has a lower frequency. Extremely high-frequency waves like X-rays or gamma rays carry even more energy, so even though photons have zero mass, they still have energy simply because they have frequency. As for momentum, quantum physics gives us a new way to calculate it. The momentum p of a photon is equal to its energy divided by the speed of light. Since energy itself is h times F, we can also say that p equals h divided by lambda, where lambda is the wavelength of the object. So, to sum it up, photons may have no mass, but they still carry energy and momentum. Their energy comes from frequency, and their momentum comes from that energy, and the fact that they move at the speed of light. Therefore, now that we've covered both massive and massless things, we need a formula that works in all cases. And that formula is E squared equals m times c squared whole squared plus p times c whole squared. This means that the total energy of any object is made up of two parts. The first part, m times c squared whole squared, represents the energy that comes purely from the object's mass, even if it's not moving. The second part, p times c whole squared, represents the energy that comes from the object's motion, or momentum. So if the object is standing still, its momentum is zero, and the formula reduces to just E equals m times c squared. But if the object is moving, or if it has no mass but still carries momentum, like a photon, then that second term becomes important. This complete version of the energy formula helps us understand all kinds of particles, in any condition, under one single rule. Therefore, now you know that E equals m times c squared is just a part of the full story, not the whole picture.